Hello.
Good afternoon, sir.
Good
Okay.
Good
How are
afternoon,
you
afternoon,
all?
sir.
sir.
How are you all? Fine.
Yes, sir.
Fine,
Yes, sir,
Uh,
fine.
sir.
hmm Okay. May I know that what we were discussing in the last class? Hello.
Sir, we discussed introduction of 8085 processor. And
Okay.
today we will discuss the 40 pins of the 8085.
Who is that? 19 number.
Yes,
Yes.
sir.
Okay. So we are going to discuss all the 40 pins that are available in 8085, and if time permit, we will also be discussing about the bus and the architecture of the whole architecture of the 8085. So I think all of you are ready for that.
Yes, sir.
So let's get started. Oh, sorry. So I am sharing my screen with you. Please let me know as you are able to see that screen. Okay. Okay. Is my screen visible to everyone?
Not yet, sir. Yeah, now it's
Now.
visible.
Okay. So I think my screen is visible to everyone. And as in the previous class, we talked about basic things related to 8085, 8085 microprocessor. Today we are going to discuss about all the 40 pins which are available in 8085 microprocessor. Okay, so these are all the 80 pins which are available. Sorry, 40 pins. I'm sorry, 40 pins which are available in 8085 microprocessor. Okay, so we are having it is definitely an 8-bit general purpose microprocessor. It can capable of addressing 64 kilobyte of memory. Okay, now can anyone tell me why it is capable of addressing 64 kilobyte of memory?
2 raised to 8, sir.
2 raised to 8 will be 64K. 2 raised to 8 will be 255. So what is the reason that the 8085 microprocessor is capable of addressing 64 kilobyte of memory?
Sir, because it has 16 address pins.
Yes, it has 16 address lines. So each address of memory location are of 16 bits. So 2 raised to 16 will come out to be 64 kilobyte. Okay, it is 40 pin, requires 50 5-volt power supply. Okay, so all these pins, they are definitely used for signaling purpose. Means already we have talked about it, that the pins generally we use in IC or communicating with the external world, and this communication definitely it would be carried out by the signaling. So this all 40 pins, they are basically grouped in 6 different group. The first is address group. So you can find it out that we are having address from 8, 9, 10, 11, 12, 13, 14 and 15. So pin number 21 to 28, 21, 2, 3, 4, 5, 6, 7 and 8. So this 8 pins, they are used as an address bus. The second is multiplex address and data bus. Okay, so as I already told you that we are going to have an address and a data line which are multiplexed. Now the whole address bus is not multiplexed with the data, because we know that we are having 8 data line. Okay, and we are having 16 address buses, 16 address lines in an address bus. So this higher order addresses means 8 A8 to 8 15 A15, they are not being multiplexed, but the lower addresses, a lower line, they are multiplexed with the data. Okay, and the signal which would be used for this multiplexing purpose is what we call it as an ALE. Okay, address latch enable. Okay, so that is a signal. So this pin number 19, 18, 17 means 12 to 19. They are used in form of multiplex address and data bus. So it can be acting as a data as well as it can be acting as an address. Okay, in the multiplexed form. The third is a control signal. Okay, so control signal consists of IO and M. So IO means IO and memory. S0, S1, we will be talking about that. That will be indicating the status. Then read, write, whether we want to have read operation or we want to have write operation. And as I already talked about ALE, that is address latch enable. So if address latch enable is equals to 1, all these pins would be acting as a lower order address of an address line. If ALE is equals to 0, whatever the thing available on these lines, they are be considered as a data. Okay, so these are the control and the status signals. Now this pin number 1, 2, 20, 40, 37, they are used for frequency signal as well as the power supply signals. Okay, so definitely we can see that this is VSS, which is 20 number, and this is VCC. VSS generally we connect it to ground and VCC we connect generally to 5 volt. Okay, and this two line X1 and X2, so between these two lines we generally use to connect the crystal. Okay, the crystal is nothing but it is generating a frequency. Okay, so anyone remember that what is the operating range of frequency that can be applied to this 8085 microprocessor? Hello? Hello? Am I audible? Hello? Am I audible to everyone?
Yes, sir.
So what was the value of frequency that can be supported by this 8085 microprocessor?
5 megahertz.
5 megahertz?
Maximum, sir.
Maximum 5 megahertz?
Yes, sir.
Let us go back and see.
3 megahertz,
3
500
megahertz.
kilohertz.
Yes, 5 kilohertz to 3 megahertz. Yes, so that is the range of a frequency that can be applied to this microprocessor, and we generally use to apply it in form of a crystal, and that crystal is connected between X1 and X2, which is pin number 1 and 2. Okay, so this frequency, yeah, it is also required by the external other devices that are connected to the microprocessor. So we will be using 37 number pin, that is CLK out, okay, clock out, that this particular pin would be providing clock to all the other peripherals that are connected to my 8085 microprocessor. The fifth group of signals, there we called it as an externally initiated signals. Okay, externally initiated signals, they are consist of, okay, can anyone tell me what are this? TRAP, RST, 7.5, 6.5, 5.5, INTR and INTR bar.
Interrupt, sir.
So yes, these are the interrupt signals. Okay, so this external initiated signals, they are interrupt signals. This is reset out, means if I want to reset the other values, the peripherals, that would be this signal would be used for resetting all the other devices. This is the reset for your 8085 microprocessor. If I want to reset my 8085 microprocessor, then I can provide a low signal to this, otherwise it will connect it to VCC. And then we are having HOLD and HLDA. These are the two signals that are used in connection to the DMA, direct memory access. Okay, direct memory access means generally what we used to have is we would read the content from IO device or from memory. We'll get the things into CPU and then again it would be provided to whatever the place it is required. But if I want to have direct access of the memory, let's say that there is another master device which is connected in the system, and that master device wants the other memory locations to access. So that can be done with help of this HOLD and HDL. This is an acknowledge signal and this is a request signal. So if any another master requires the address or a data bus, it would be providing hold signal to this 8085, and once the 8085 reaches gets the hold signal, it will come to know that yes, I need to release my data and address buses for this particular service, and it will acknowledge the device which is providing or giving an HOLD signal to 8085 by HLDA signal, and it will release the address and the data bus in the after the current execution of the instruction is completed. Uh, and then we are having a serial IO. Okay, so we can also connect serial devices over here. So this is a serial in, serial out kind of a signal. So yeah, you can have a serial communication that can also be carried out with 8085, and the pins which are used for serial communication is pin number 4 and pin number 5. One is SOD, serial out data, SID, which is serial in data. So these are the different 6 groups in which all the signals are being divided, or the 40 pins are being divided. So let us try to see all the groups one by one. Am I clear up to here?
Yes, sir.
Yes, sir.
Okay. So we are having 16 signal lines that are used as an address bus. Oh, this is being splitted into two different divisions or two different sections. Okay, there are split in two segments. One segment is A8 to 815, and another segment we called it as an AD7 to AD0. Why AD7 to AD0? Already I have talked about that. It is used in the multiplex form. Okay, so 80 to A15 to A8, 8 to 15, they are unidirectional and used to carry the higher order address of the 16-bit address. Okay, so this is the higher order address, okay, of the 16-bit address of a memory location. And this 87 to 80, they are used for the dual purpose. One is for the lower order address of 16-bit address, and another it can also be used for the data. So this as it is being used for the data is a bidirectional. Okay, so this 87 to 80, they are bidirectional and they use for the dual purpose, one for data, another for lower address of the address, lower order of an address. Okay, so the lower order address can be separated from the signal by using a latch. We called it as an address latched enable. So this is a signal we already talked about, that there is an address latched enable signal which is used for that particular thing. The second is the control and the status signal. Okay, so there are two control signals. One we called it as a read and another we called it as a write. Okay, so generally we used to read the memory or read the IO, as well as we can write the IO and write the memory also. Okay, so this particular signal will help us to identify what operation is to be carried out. Means, let's say first of all I have kept the address onto the address bus. Okay, by enabling my data address latch enable signal to 1, so address is identified, and then I'll keep the data. Okay, so if I'll cap the data, then if I'll pull this particular WR line low, then the data would be written into the memory, and if my read signal is being kept low, then the memory would be providing the data onto the data line. So this is how the read write signal would be used. Okay, there are other status signals. One we called it as S0, S1, IO and M. Okay, so whether you want to read your IO section or whether you want to read your memory section. So if this signal is being kept low, it would be reading the memory section. If this signal is equals to high, then it would be reading the IO section. Okay, and we are having ALE signal, address latch enable signal. So if this ALE signal is equals to 1, I'll be considering whatever the thing which is available over here as an address, and if it is 0, I'll be considering it as an data. So this ALE, which is pin number 13, It is a positive going pulse generated every time 8085 begins the operation. This is what we call it as a machine cycle. We would be shortly discussing about a machine cycle, T states and operation code and all that thing later on. Okay, so it indicates that the bit D7 to AD7 to AD0 are the address. If this is a positive going pulse, if AL is positive going pulse, D7 to D0, it is a part of an address line. Okay, so this signal is used preliminarily to latch the lower address from the multiplex bus and generate the separate set of lines, that is A7 to A0. This read signal, which is 32 pin number, this is read control signal, which is active low. If there is a bar, we can call it as an active low signal. Means yeah, whenever it is pulled down, then that particular task is carried, active low. So this signal indicates that the selected IO or a memory device is to be read and a data is available on the data bus. So this particular thing indicates that it is a read operation. Okay. 31 is a write, so it is also an active low signal. Okay, and this signal indicates that the selected IO or a memory device is to be written and data is available on the data bus. So whatever the data is available on the data bus, that must be written into your memory or an IO section. So pin number 34, that is IO or memory. So this is a status signal that is used to differentiate your IO and memory operation. Whether the microprocessor is going to carry out an IO operation or whether it is going to carry out the memory operation, that is being differentiated by this pin number 34. So when pin number 34 is low, it is IO operation. Okay, and whenever pin number 34 is whenever pin number 34 is high, it is IO operation. And when the pin number 34 is low, it is a memory operation. So this signal is combined with a read write to generate IO memory control signal. So which memory, whether you are going to read or whether you are going to write into IO section or a memory section, that is going to be defined by pin number 34 and 31 and or 32. So this S0 and S1, these are the status signals that identify various operations. So these are the various operations that are being identified by S0 and S1. So S0 and S1 combine to generate this particular signals. Okay. So if S0 and S0 S1 they are 0 0, it is halt, means you do not have to do anything. If it is 0 1, then it is in the write mode. It is 1 0, then it is in read mode, and 1 1, then it is opcode fetch. Okay, now opcode. Do you know what do you mean by an opcode? Hello? Hello, am I audible to everyone?
Yes, sir, you are audible.
Okay, so do you know, have you heard about opcode? Opcode. Do you know what do you mean by opcode? Hello? Opcode, have you heard about it anywhere?
No, sir.
Okay, now I think all of you would have heard about instructions, that if I want to, if my processor wants to carry out anything, then it must be given an instruction. Okay, so instruction is nothing but let's say that I want to uh, copy a data from one memory location to another memory location. Let's say we talked about register only. I want to copy it data from one register to another register. Let us say that I want to do copying of data from C register to B register. So I'll be using a instruction that is move B to C. Okay, so this is what we called it as an instruction. Okay, now we understand move. Yeah, definitely the name itself suggests move, M-O-V, move B comma C. If I write something like this, then we can understand that it is move operation from B to C. Okay, now the same instruction is to be provided to the microprocessor. Now microprocessor don't understand what is MOV or B or C. It don't understand that thing. So it would be understanding it in form of 1 and 0. So let's say we code it. Okay, let's say 75. We code it 75, that MOV BC is a 75. So if I provide 75, then whatever the 75 that is I'm talking is what called as an opcode. Okay, that would be an opcode for your microprocessor. Okay, for a simple example, whenever I write a program, then at an end of a program I must be writing an instruction to tell microprocessor that now this is an end of a program. So there is always an halt instruction, HLT is an halt instruction, always being coming at an end of the program. So HLT, so I can understand HLT is an halt, but microprocessor will not understand HLT as an halt. So I'll be coding it in form of some value that can understand by microprocessor. So I'll be considering it as 76. So whenever microprocessor comes that opcode is 76, it will have the halt operation. Okay, so they are what called as an opcodes. Okay, so if whenever your processor is executing instruction, whenever you want to fetch an opcode, fetch means to take the opcode into my microprocessor. Okay, so your S0 and S1 must be equals to 1 1 at that point of time. Okay, so that is what called as an opcode fetch. Okay, so these are the combination of IO, read and write. Okay, so if all these three are 0, it is halt. Then if it is 001, then it is uh, memory read. Then it is memory write. This is opcode fetch. Again, this is halt, IO read, IO write, and 111 is NOP. So this is how generally the uh, signaling is being carried out in our 8085 microprocessor. Okay. The other section is power supply and your frequency signal. So we talked about that you are having two pins, pin number 40, it is for VCC. So we know that our microprocessor 8085, it's operate on 5 volt DC. So this 5 volt supply we will be providing at pin number 40, and the ground of this we would be providing it to VSS, that is the ground reference to the microprocessor. Okay. Then we are having X1 to X2. So X1, X2, that is pin number 1 and 2. Crystal oscillator is to be connected to between these two pins. Okay. The frequency is initially divided by 2. Okay. So the operating frequency of your microprocessor is we have already discussed that it is 6 megahertz. Okay. Now it is being initially divided by factor of 2. Okay, and therefore the crystal which must be connected to your microprocessor must be of 6 megahertz. So whatever the operating frequency you want to keep, let's say if you want to have 500 kilohertz, then you need to have the crystal connected to between X1 and X2 must be of 1 megahertz. Okay, now there is a logic why we used to have the frequency divided by 2. Okay, because because of the duty cycle. Okay, now it may be the case that the crystal which is connected may not be generating an exact duty cycle of 50%, but my microprocessor requires exactly the duty cycle of 50%, okay, for its operation. Okay, so that's why generally the frequency is being divided by 2, means one clock cycle would be for positive age and one clock cycle would be for negative age. So exactly I can make my my duty cycle 50%. Okay, so that is why it is initially being divided by 2. So if you want to have the system operated at 3 megahertz, the crystal that must be connected to your system must be of 6 megahertz. Am I clear? Hello.
Yes, sir.
Okay, so this is a Viva question generally being asked, that why the frequency is divided by 2. So at that point you may be able to give an answer that to get an exactly 50% duty cycle we used to divide the frequency by 2. Okay, so if you want to operate your microprocessor at 3 megahertz, then the crystal must be connected to the crystal, the pin number 1 and 2 must be at 6 megahertz. The other is a clock out signal. So clock out, it is pin number 37. This signal is used as a system clock for the other IO devices for synchronization with the microprocessor. Okay, so you also need to provide a clock to the others. So and we know that the clock is generally used for synchronization purpose. So yeah, the clock must be from out from over here. Then we are having interrupt. Okay, so one is INTR. Okay, it is used for general purpose interrupt. And INTA, it is interrupt acknowledgement. Okay, so what do you mean by acknowledgement? So other interrupts, they are not acknowledged, but INTR, it is an acknowledged interrupt. Okay, so whenever the INTR signal becomes 1, okay, and a microprocessor come to know that it is an interrupt which is being generated at this pin, so it would be acknowledging with pulling this INTA signal low. So the other peripheral which has generated an interrupt will come to know that 8085 come to know that there is an interrupt. Okay, the other interrupts, they are RST 7.5, RST 6.5, RST 5.5. Okay, they are what we call it as a restart interrupt. So these are vector interrupt that transfer the program control to the specific memory location. Okay, now it is very important to understand that how interrupts are being handled. Okay, so generally interrupts are handled by microprocessor by running a code. Okay, so whenever you are having an interrupt, let's say you are having an interrupt 7.5, so there will be a specific memory location, okay, where you will be writing the code for this int 7.5. Means let's say that if int 7.5 is being received by microprocessor, it needs to erase all the memory, or it needs to stop the execution, or whatever the task that you have specified, that whenever this interrupt occur, this must be the task that must be performed by the microprocessor. Okay, so that particular thing is being located at a particular, written at the particular memory location. Okay, so that's why they are called as a vector interrupt. Vector interrupt means it is having a specific memory location where the interrupt subroutine, we called it as an interrupt subroutine, that is being written. So whenever the interrupt occur, the program counter is loaded with the value which is corresponding to that interrupt. Okay, so that's why they are what called as an vector interrupts. This 7.5, 6.5 and 5.5 have higher priority than INTR. Now what do you mean by priority? So a service is to be provided when interrupt is requested. Okay, so when there is an interrupt request, then the service is supposed to be provided by the microprocessor. Now many of time there would be a condition whenever there may be a condition that two interrupts may be coming at the same point of time. Okay, Now microprocessor will get confused that which is an interrupt I need to give a service first. Okay, so the priorities are being defined. So the 7.5, 6.5 and 5.5, they are having higher priority than INTR interrupt. Means if INTR interrupt is there, at the same time if RST 5.5 or 6.5, 7.5 is there, then service would be provided to 7.5, 6.5 or 5.5 instead of INTR. Okay, so that is what we call it as a priority of the interrupt. Okay, among these three interrupt, the priority order higher to lower is 7.5, 6.5, 5.5 respectively. So if I'll go for the priority, then the highest priority is to 7.5, then comes 6.5, then 5.5 and then INTR. There is another interrupt which is having higher priority than this also, which is non-maskable interrupt, and that is trap. Okay, so this trap is a non-maskable interrupt and it is having an highest priority. Now non-maskable interrupt and maskable interrupt. Non-maskable interrupt means you cannot ignore this. Okay, and maskable interrupt means you can make them silent also, that I don't want to take an interrupt at this point of time. Okay, you can mask them, you can suppress them. Okay, by setting a bit in your 8085, you will be able to suppress the interrupts. Means the interrupt is not being taken by 8085. Okay, but trap is having an highest priority and it is non-maskable. You cannot mask this interrupt, so this interrupt would be there, means it cannot be masked. Okay, then we are having HOLD and HLDA. Okay, so HOLD is an input, means it would be taken into a 8085. So this signal indicates that a peripheral such as DMA means direct memory access control, okay, is requesting a use of address and the data buses. And HLDA, it is an output signal which gives an acknowledgement. Okay, so if any peripheral request the DMA, okay, means if any peripheral wants to use this address and data bus, okay, then it will be providing an HLDA signal to your 8085. Okay, and if 8085 recognize the signal, it will be providing acknowledgement to the that peripheral with help of HLDA signal. So hold acknowledgement, this is a signal to acknowledgement hold request. Then there is an external initiator signal which is a ready signal. It is a type of an input signal. So this signal is used to delay the microprocessor read and write cycle until the low responding peripheral is ready to send or accept the data. Now it may be the case that whatever the peripheral that are being connected to your 8085 may not be operating at the same speed the way 8085 may be operating. Okay, or your CPU is operating. Okay, so this particular signal means the ready signal will be used for synchronization of these two particular peripherals. So this signal is used to delay your microprocessor read or write cycle, means it will be extending the read and write cycle of your microprocessor until the other peripheral is ready to accept the data or to send the data. Am I clear? When the signal goes low, the microprocessor wait for an internal number of clock cycle until the ready signals becomes high. So it is predefined that this many number of clock cycles it must be waiting until the ready signal once again goes to the high value. Okay. Yes, anyone wants to ask anything? Okay, let's move further. And these are the two reset signals. So resetting, it is an input active low signal. So when signal on this pin goes low, the program counter is set to 0 and the buses are tri-state and microprocessor is reset. Means it is as good as you turn the things off and again you turn the thing on. So that is what we call it as a reset. So many time when we find it out that our microprocessor has gone into an infinite loop, we may be providing a reset signal to the microprocessor to initially get our program counter to the 0 value. So again it will start up with the 0 and all the operations will be carried out once again. Okay, and reset out, this signal indicates that microprocessor is being reset. So this signal is also used to reset the other devices, means all the other devices are also being connected to the microprocessor. If microprocessor get reset, the other devices must also be indicated that yes, the microprocessor is get reset. So to reset all the other devices, the microprocessor generate a active high signal which will reset all the other devices which are connected to the microprocessor. Then we are having SID, SOD. Okay, so these signals they are used for the serial communication with the microprocessor. So in serial transmission, data bits are sent over a single line, one bit at a time. Okay, so yeah, we know that parallel communication. I think all of you know what is parallel communication, serial communication. Yes. Hello. Hello, am I audible to everyone?
Yes, sir.
So I think all of you are knowing what is serial communication and parallel communication.
Yes, sir.
Okay, so in serial communication we use only two lines, and maybe in some case we can use three lines also. Okay, so one line is for to get the data in, one line is to get the data out. Okay, and it would be done one bit at a time. There would be a serial register that is associated with this SOD also. Okay. So this is how all the pins of your 8085 microprocessor are organized, and we have discussed every pin of our 8085 microprocessor. So if you are having any doubt related to any pin that I have discussed up till now, you are free to ask. Hello.
No, sir, no doubts up till now.
Okay, so there is internal architecture of our. I'll be showing you the internal architecture of the whole whatever the things that we have seen in form of pins and all that thing, how they are being connected to each other. Okay, so this is the whole 8085 uh, internal architecture. Okay, I think we must stop at this point of time, and in the next class we will try to discuss the whole block diagram, internal block diagram of our 8085 microprocessor. Am I clear?
Yes, sir.
Yes, sir.
Okay, so if you are having any kind of doubt, you are free to ask. Otherwise, that is all from my side. In the next class, we'll be talking about what the thing I have shown you in the form of an block diagram and internal architecture of your 8085 microprocessor. Okay. Is it fine?
Yes, sir.
Okay, so thank you all. See
Thank
you in
you,
the
sir.
next class. See you in the next class.
Thank you, sir.
Thank you, sir.